So Rob and I are going to talk about the invasion of these funny little machines called Automata. This cute little picture. This invasion has been happening quietly for the past few months in Lucene. Here's a quick outline. We'll introduce ourselves quickly. Then we'll give an overview of what finite state technology is at a theoretical level. Then we'll talk about the 3 implementations that we have in Lucene's base APIs that provide support for this technology. And finally, we'll spend most of our time touching on some of the applications in Lucene that have made use of finite state technology and the benefits we've seen from that. My name is Mike McCandless. I'm a Lucene and Solar committer and a PMC member. I've been at this for 6 years now. I think that qualifies me as an old hat. I'm also co-author of the 2nd edition of Lucene in Action. And I have a blog where I write about interesting Lucene topics every so often. And I would like to thank IBM for sponsoring all of my open source efforts.
And hi, I'm Robert Muir. I'm younger and been around Lucene a little bit more recently, but I have a background kind of working with this stuff, NLP and things like that outside of Lucene, and one of the first things I tried to do was kind of start combining these things. So I'm really excited about some of the progress we made. I don't have really a blog on Lucid's website. I blog sometimes, but I have a Twitter account. So again, diving in, we're going to start with an overview of what these data structures are. And we're going to do that. That kind of has nothing to do with Lucene, but just to kind of set the stage. So the first thing we'll talk about is the finite-state automata. And this is basically a machine. It accepts strings. That's the purpose of it. And it doesn't really have to be a string. It can be numbers, can be kind of symbols is a good way to generalize it. And we have an example one here in this picture and a list of words that it will accept. So basically, it's a binary decision, yes or no. And what you do is you start at the little arrow at the start state, and you kind of accumulate characters as you go until you reach the end, the final state. And that's all these things do. I guess the great thing about them is you can do a lot of operations on these things, and you can transform them in different representations. And so some of these we'll talk about later, but they're useful for queries, especially. Now, a transducer kind of extends this concept a little bit more, and now we have something that's more kind of like a map, because we don't just accept input strings, but as we're accepting them, we are producing some kind of output, right? So this is kind of like hash set versus hash map or whatever in Java. And the cool thing about this is that the output, here we have some numbers, and as you walk through it again, you add up the numbers, but that's kind of the algebra, they call it, and this is pluggable. Like, we could actually have a machine that writes out letters, and we use append to create an output string from an input string or whatever. So you can kind of plug in a different output format, and by doing that, you can solve different kinds of problems. This is just a very simple example. And there's a lot of theory behind this, a lot of operations that are well-defined that we can use for different purposes as well.
Many papers with many large Greek letters.
Yes.
Hard to understand. Okay, so that was the quick introduction of the abstract notion of a finite-state automaton and a finite-state transducer. Now we're going to jump in and see how we've implemented these data structures in Lucene's base APIs. So for finite-state automaton, we actually poached a nice package, the bricks package, from the bricks.tk package. We pulled that into org.apache.lucene.util.automaton, and we've modified it quite a bit and added tests. It's a very approachable, very easy to understand API. You can build any automaton one node and one arc at a time. It's kind of like working with Tinker Toys. There are no restrictions on what you can build. It can be non-deterministic, deterministic. It could have cycles. It could be disjoint. It could be minimal or not. You have complete freedom to build it up. It's very flexible. The package comes with a bunch of standard operations. Minimize will take an FSA and produce another FSA that's perhaps, which is the smallest FSA, that will also accept the same set of strings as your original one. Determinize ensures that every node has only one arc for a given label, so that if you want to walk through the FSA, there's only one path to do so. Intersect and union, those are straightforward operations. You can take a regular expression, a string, parse it, and produce the corresponding automaton that will accept that regular expression. So it's a very useful API. And once you have your automaton, you can construct it. You compile it into a run automaton. It's sort of like Java's matcher. If you have a pattern, you produce a matcher from it, which can quickly step through a string and check if the automaton accepts the string. Side by side with the automata package, we have the FST package. The FST package is somewhat polar opposite of the automaton package. Where the automata package has nice objects and you can build an arbitrary machine up, the FST has a single byte array. The entire machine is represented as a single byte array in memory with all of the arcs stacked next to each other and encoded in a compact format. Whereas with FSAs, you can build an arbitrary machine. With FSTs, we have only one way to write an FST, and it writes a very specific kind of FST, a kind that's very useful for Lucene. And that algorithm, it was implemented from a paper by Mehoff and Morrell. It requires that you take a pre-sorted set of inputs and their corresponding outputs, and then add those inputs in order to a builder, and then the builder will incrementally produce this byte array as it's going. The algorithm is quite fast. It's linear in the input size on the net number of characters of your inputs, and it has a fairly low memory overhead. There's an integer hash table that has to keep track of states, but even that hash table, you can dial it back if you want to reduce the amount of memory that's in use. You can dial that back and have a not quite minimal but still fairly small FST. So it's fast, it's low memory, and if you are very interested in producing the smallest FST you can create, there's an optional two-pass process which will spend more memory and more CPU, but then produce an FST that's maybe 25% smaller. When you want to operate with the FST, when you want to read it and check whether a given input is accepted and what output it maps to, there are APIs to decode one arc at a time, and you sort of step through the FST decoding from that big byte array, where, each arc that leaves a certain node and checking whether the label matches what you're trying to find. And so the FST acts like a sorted map. Because you added the inputs in sorted order, the arcs that leave each node are also in sorted order, which allows us to implement operations like seek ceiling. So you can find the ceiling term, you can find the floor term. Once you find those terms, you can iterate in order. And so it behaves like a sorted map. There is one downside to the FSTs. The generics policeman does not approve of the APIs. In fact, when I produced the first patch for FSTs, I was all excited. Everything passed. I had a nice, wonderful random test. I was excited I was going to commit it. And uwe comes in and says, the test case needs to be rewritten because it does not use generics properly. And I hope you're all following what uwe says on Twitter. If you're not following it, then you're not using Twitter correctly. So the final base API that we have in Lucene is actually an unexpected one, TokenStreams. It turns out that Lucene's TokenStreams produce an automaton, and you wouldn't expect it. Normally you think of the TokenStream, and by the way, the TokenStream is the class that produces the set of tokens during indexing. So the analyzer will take a string and enumerate a set of tokens. TokenStream is the class that we use to do so. Normally you think of the tokens as a single linear chain of tokens, but you can actually think of each position as a node, and each token as an arc, and then you actually have a graph. And so if you have a synonym filter that inserts fast whenever it sees quick, the graph is interesting because you've got two tokens at the same position overlapping each other. And then in 3.6, we added a new analyzer attribute called the position length attribute. This records the number of positions that a token spans. So we already have position increment that tells you where the token starts. Now we have position length that can tell you where the token ends. And this gets more interesting with SynonymFilter. For example, if you have a synonym that detects wireless network and injects hotspot, now hotspot will record the fact that it spans two tokens. We have a useful method to convert a token stream to an automaton. It lives in a patch. It hasn't quite been committed yet, but it's there because the two data structures are actually equivalent. And so token streams are really a streaming FSA. You get one arc at a time, but otherwise it's equivalent with an FSA. It's going to be a lot of work to make all analyzers work correctly with graphs. So if you start combining together interesting tokenizers and token filters that produce graphs, you might want to jump on the list and check if everything is going to work correctly because it's a fairly large amount of work.
Okay, as Mike explained, we have 3 different implementations. So what are we actually doing with these things? You know, what are the applications? Why are we adding them? Why are we extending them? And that's basically what I'm going to explain. I'm going to start with kind of whole different types of applications we have in Lucene. Some are more low level, some are more high level, some solve totally different problems, different languages, and we're going to explain why these things are useful and kind of what benefits we're seeing. So the first thing we added was actually to use the FSA as AutomatonQuery. And all this does is allow you to take any automaton and match documents that accept those terms. So we were able to refactor kind of some existing queries that we had in Lucene, like wildcards and fuzzy query, to use this to be represented as automatons. And we actually get, we added regular expression query since we already have this regular expression support from Bricks. So basically, this gives us one code path for these things that is very efficient, and you see some speed up boost in Lucene with these. You also, it makes the queries a little bit simpler because the matching and the parsing are completely separate. And there's other possible uses. It's very easy to extend this class, and you could make your own kind of pattern matching queries if you wanted to. So for example, you want to do stemming via expansion rather than reduction, you could do that. It might be a way to go. This is just kind of a joke as we talk about the fuzzy query. Mike's already mentioned certain papers involved in this stuff, and this one in particular was 67 pages long. It had 9 chapters. So I kind of stole a slide from somebody that was doing a talk on Java 7 bugs, and basically he said how to debug hotspot hands-on, and he had this slide, and then the next slide looked like this. But it's kind of similar, right? Like dealing with these papers is kind of like working with a hotspot bug or something like that. So in this situation, there was a lot of staying up late at night. I know Mark Miller helped, and I helped, and we got some people that aren't even associated with Lucene helping us debug these things, like a guy that's a video game developer, a couple other random guys. But you know, we finally got through it. We got Mike involved at the end just because we somehow involved Python. So you know that suddenly he was sold. But yeah, so this is kind of what fuzzy query looks like now. And so we generate this automaton. This is actually dogs. So if you want to find the misspellings of dogs, we generate this thing, and then we intersect that with the terms dictionary. And so there's a link here. Mike has a blog that describes in more detail this crazy story of involving Python and video game developers and pulling our hair out and everything like that. And this 9-chapter, 60-page paper. But yeah, basically it's hairy. We got through it. We have good tests, and this is just one application.
And it really is 100 times faster than 3.x, sometimes 200 times faster.
So now that we can do a fuzzy query, I mean, what could we do that's even more useful maybe is to not even do the query and just to do the spell correction, right? And just to find those terms that we corrected. So before, Lucene has a spell checker in the 3.x branch that is it builds a separate index. So this can kind of be a pain for you. Like you just have 2 indexes to manage instead of 1. And so the idea was, well, why don't we just use our fuzzy query that we already just did and spend all this time on to do this spell correction? Well, at first it wasn't very fast. It wasn't fast enough, I think, for spell correction. But what we did is kind of let the patch sit out there, and Mike rewrote the term dictionary a couple times, and each time the speed would get twice as fast. And finally, now it's on our Wikipedia corpus, we can do close to 50 queries per second. And Mike's going to explain a little bit later exactly how we got that high, but it's basically improvements to the index structure, Lucene. This quote here, I'm confident in 3 weeks I'll be done, is because in order to do the spell correction, we actually want to handle transpositions as well, just like any other edit distance operation. And so this required another chapter in the paper to be solved. And so our friend helping us from the video game industry, he sent me this email and he said, it's going to take me 15 hours to write this algorithm and I'll be done in 3 weeks. I'm confident it'll work. And which is, if you look at the math involved, it's kind of crazy that someone could have a software estimation like that. But
and he was done in 3 weeks.
And he did do it. Japanese analysis, kind of a completely separate use case. There was just a talk on this Christian just gave, great talk on it. But just to talk about kind of at the low level, we use the dictionaries, both the user dictionary and the IPADIC statistical model that ships with this thing. We have FST data structure for these. So this means you can have like a very large user dictionary. It will scale well. And it means that we have a nice compact form for the system dictionary we ship, which is pretty big because it has a lot of words, it has a lot of probabilities, and we managed to get the jar file pretty small. I think this is almost 12 times smaller than the existing data structure, which is double array tree. It's actually kind of an automaton itself, but the FST was pretty fast, surprisingly fast, and we were able to save a lot of space this way. By doing this, by implementing this FST, it actually encouraged Mike to then go and do crazy improvements to the Viterbi search and to do the streaming API and all kinds of other improvements that have made this Japanese analysis really cool. And one example is that there's a compound word problem similar to German and other languages in Japanese. And so as it's doing the segmentation, it's also decompounding these compound words at the same time and offering alternative analysis. So it's kind of creating synonyms. In this case, we have shopping center, and we create that as one word, but then as synonyms, we also supply shopping and center separately. So this is kind of an interesting use case of FSTs. Like I said, seeing the improvements over the other data structures was nice. Having the user dictionary have the same runtime as the system dictionary means that when you extend it, you don't have to worry about performance getting in your way. So it was a good fit. And then kind of the most recent use case is in query suggesters. So there's a talk about auto-suggest. Actually, I hope you saw that as well. But we've kind of been making a lot of improvements around query suggesters because here what you're trying to do is the user is going to type in a couple characters and we want to complete it with the most relevant query that starts with those characters. So one good data structure for that, since we have this kind of map, this input and output, and the output is the weights and the input is the queries, is to put them in an FST. We have two implementations here. The first one we have is called FSTSuggester, and it works a little bit differently than the second one we have, which is WFSTSuggester, which is a weighted transducer. Basically, at the end of the day, they're both going to give you the same results, but the method in which they use to do this is different. The FSTSuggester is actually an FSA. It's actually an automaton. It has no output in the FST. All it does is basically you supply weights, and it buckets these weights and creates that many FSTs and just traverses each FST in order. The WFSTSuggester, we kind of looked at our FST and said, can we do weighted FST operations? We didn't really know if we could. And so we decided to try it out, because if we could, then we could have more fine-grained weights rather than this bucketing. This would give the ability to have kind of all the scoring you want. So this was the quote when we first started talking about this from David Weiss. He said, I don't think this will work, but I can't provide a counterexample right now. So when we started talking about the math behind this, but imagine this is your query suggestions. You only have 5. And in this case, what we say is the lower weights are better. They're like costs. And so this is what the WFST, a weighted FST, would look like here. The key is how it pushes back these outputs to create weights, which makes them more useful. For example, at the very beginning, we can see that the smallest weight, just by looking at the first node, is 1. We know the smallest weight for the entire suggester. So for that, we could actually take no input and say, here's the top queries or whatever in ranked order. But yeah, basically what you would do is if you wanted to complete WEA, you just walk the prefix for that, and then you do a shortest path. You follow the costs along the shortest path. So we do something you couldn't ever do with, like, say, a hash map, is we walk the inputs for a little bit, and then we just switch over to walking the outputs. And we do this, we find the n shortest paths. If you want 5 suggestions, we find the 5 shortest paths here with the least cost to give you back your suggestions. So this is new in 3.6.
SynonymFilter. So let's see. SynonymFilter is what you use to detect multi-token sequences during analysis. So if you want to recognize Wi-Fi network and output hotspot, you would use SynonymFilter. You give it a bunch of rules, and it will start up, load those rules, and process the tokens as they come through the stream. You can apply the synonyms at index time or at query time or both. There are lots of tricky trade-offs if you do so, and there's no quick answer about what's the right way to do it. So jump on the lists if you have problems doing that. The first version, the original version, used recursive hash maps, and it was a sort of a big data structure. And then in 3.4, we cut it over to an FST. And this provided dramatic improvements. We got a 5-fold improvement on the filtering rate, so how quickly it can process the tokens, a 14 times faster startup, so that if you have a lot of rules, the time it takes to compile those rules to the FST got 14 times faster, and a tremendous reduction in RAM because the FST is such an efficient structure, a single byte array. So if you're using SynonymFilter on a large set of synonyms, it's very much worthwhile to upgrade to 3.4. There are caveats. If you have a synonym rule that matches and then outputs more than one token, for example, you match DNS and then output domain name service, that actually is going to mess up the token graph because domain will overlap with DNS and then name and service will hang over and overlap on the next two tokens. So phrase queries aren't going to work correctly. So that's one caveat to be aware of. Also, while SynonymFilter produces a token graph now in 3.6, it sets the position length attribute so that a hotspot is spanning 3 tokens. It cannot actually consume one. So if you put Kuromoji's Japanese tokenizer in front, or you have another SynonymFilter in front, or Shingle filter or WDF filter, it's going to have problems. You won't get proper matches in that case. So there are some trickinesses. But finite-state technology touches SynonymFilter in 2 ways. First of all, we cut over to FSTs, and second of all, it actually produces a token graph now. So it's a double whammy. So this next change, before I describe it, I wanted to show the performance graph, the dramatic improvement that we got. Rob referred to this earlier in the DirectSpellChecker. This is a graph that was generated from our nightly performance benchmarks. We have a set of scripts that every night checks out Lucene sources, does a bunch of rigorous tests. It takes like 3 hours, and then produces another dot on this graph. So this has been running for over a year now. And so back in August of last year, when we committed BlockTree, we saw a massive improvement in the DirectSpellChecker performance because that DirectSpellChecker is very intensive on the terms dictionary. And so how did that happen? So stepping back a bit, the purpose of a terms dictionary is to record every single unique token that was seen during indexing, store it somehow in an efficient way along with its metadata, such as the document frequency, the total term frequency, pointers into the postings file. So there's a lot of metadata that's stored. And it has to store this so that it can be efficiently accessed at search time, like a sorted map. You have to be able to jump to a particular term, and if you found the term, retrieve its metadata. If you didn't find the term, maybe you want to iterate from there on the terms in sorted order. With Lucene 4.0's codec architecture, it's fully pluggable. So you can swap in different terms dictionary implementations. Because in general there can be a huge number of terms, we know of at least one case that has billions of unique terms, you can't store them all in memory necessarily. Some applications can, but in general you can't. And so BlockTree, just like 3.x's terms dictionary, takes the terms and groups them into blocks. So in 3.x, it's every 32 terms. So every 32 terms, it's a very regular interval, creates a new block that's put on disk. And then in memory, there's an index that points to those blocks. So when you want to look up a certain term, you look in the index, you figure out which block to go to, you do a disk seek to that block, and then you scan looking for the particular term that you want. The difference with BlockTree over 3.x's approach is the blocks are now variable sized. Instead of every 32 terms, it's now allowed to range between a minimum and a maximum number of terms per block. And that additional degree of freedom is very important because it enables BlockTree to assign terms to blocks based on their shared prefixes. So if you have a whole bunch of terms that start with http://www, because your tokenizer didn't strip those things off, then those terms can be assigned to their own block or set of subblocks. And there are some very nice properties that come out of blocking the terms in this way. You get a very fast intersect method, which can look at the index in memory, which is an FST, and do the intersect of an automaton with an FST to identify the possible blocks that might have matches and require further scanning. Furthermore, unlike 3.x, based on the index, you can determine that it's not possible for a certain term to exist. So when you go to look up a term, in 3x, you always have to go seek to disk and scan the block to see if the term's there. But with 4.0, in certain cases, we can just by looking at the index know that there's nothing to scan to. The paper is hard to understand. The source code is even harder to understand. So I thought I'd walk through an example because I think BlockTree is actually a very simple concept. It just doesn't render well on paper and bits. So here's an example. You can think of it like a game. You are given a whole bunch of terms, and it could be hundreds of millions of terms, but I've got like 12 or 13 terms here. And the game is this. You have to break these terms into blocks such that there is at least 3 terms in a block and at most 4. And that number 3 and 4 are parameters you can specify. I think the defaults are 25 and 48 right now in Lucene. And so it's actually a pretty straightforward game. You have to break them out by shared prefix. So I see that I have 3 terms that have A, and so I'm just going to pull those 3 terms out. So when I pull those out, I keep the A prefix in the original block, and then I'm pointing to a subblock that only has the suffixes. And so now one block is OK. I've got 3 terms, but I still have the root block, which is too large. And so now let's pull out all the terms that start with P. So now the root block is actually OK. It's got only 3 entries in it, and the A block is OK. But now the last block is still too large. And so I see RE and RO are the prefixes I can factor out. And so I'm going to factor those out. And so now the game is done. This is what the block tree index looks like for this set of terms. I have one block that has 4 entries, and then the rest of them have 3 entries. And at this point, that's what I'm going to write to disk. And then I build the index, which is an FST. And so the index holds the address of each block, where the address is the string prefix that led to that block. So for example, this FST accepts the empty string for the root block. It has A, it has P, and PRE, and PRO. And now when I need to look up a term, let's say I want to look up the term precious. So I look at the index. I look at the FST, I traverse it, PRE, and that I sum up the outputs, 31 plus 10, 41. 41 is the address on disk that I have to seek to. So I then seek to 41, check if precious is there, check if CIOS is there, IOUS is there, and it's not there, so I know the term wasn't there. If I try to look up price, I go through the same process. I step through PR. When I get to that node, I see that there's no I leaving. There's only E and O. And so at that point, I actually know that the term price was never indexed. There are no PRI terms in this index. And so right away, I can return that there's nothing there without having to do a disk seek. So those benefits of having the prefix in memory as an FST is what gives us a huge boost on our intersect performance. OK, MemoryPostingsFormat is another change that was touched by finite-state technology. Once again, we saw an awesome performance improvement. And I'll describe how that happened in a second. But this graph is showing the primary key lookup performance. And both of these graphs are showing the performance of a single thread. So if you have multiple threads running, they scale up linearly, I hope. And so around July of last year, we switched over in our nightly benchmarking. We switched over the ID field for our index to use the MemoryPostingsFormat and saw a substantial improvement in performance. And so what MemoryPostingsFormat does is it stores everything in an FST. So I just got done explaining how there are too many terms and you can't store everything in memory in general. Well, in those cases that you can, such as your ID field or maybe date filter fields, MemoryPostingsFormat is a great fit. It accepts everything that's being indexed. It puts the terms into the FST as the input, and then it maps as the output, because the outputs are pluggable, it maps it to a byte array. And so that byte array encodes the same postings that would have been written to disk, but it's actually stored in the FST instead. So because everything's in memory and because we're using an FST, we get a nice performance improvement. When you start up your searcher, it's going to load that FST into memory and serve all queries from there. And once again, because of the 4.0 codec architecture, just like the terms dictionary is pluggable, you can also plug in different postings format on a per field basis. This is not a good fit for fields that require skipping because it doesn't have a skipper yet. It just does a linear scan. So if you're doing AND queries or anything crazy like that, don't set that field to be the MemoryPostingsFormat. Okay, so that we sort of touched on a bunch of places where we're using finite-state technology. There are also a bunch in progress or ideas we have here. Mapping car filter. This is a car filter that you run before your tokenizer that can replace character patterns. It's sort of like SynonymFilter, but for characters instead. When it detects a pattern, it replaces it with the replacement and properly preserves offsets so that highlighting will still work correctly. This is no longer in progress. It was committed earlier this week. Field cache and doc values. In field cache, you're able to load terms or a terms index, which is able to tell you a term for every document in your index. It's a single valued field, so you can look up the particular term for any document. Currently, that's stored in a fairly inefficient straight structure. We just duplicate all of the terms we saw, the unique terms, so it's not as bad as it could be, but still. We can get some good performance improvements and RAM reduction by just storing those in an FST. And this actually relies on the reverse lookup. If you have an FST and the inputs have to be sorted, but if it so happens that the outputs are also sorted, which is not required, But if they are, for example, term ordinal, the first term goes to 0, the second one goes to 1. If your outputs are sorted, you can also look up, do a reverse lookup. So given an ordinal, you can find the term that has that output. So that the prototype patch that we have there relies on that capability of the FSTs. Another idea we've batted around, but there's no patch out there yet, is just like you have AutomatonQuery, which will let you match all of the terms that the automaton matches, all the documents that match those terms. Perhaps you want to assign weights to those because you want to give a different boost to different terms. So if we had an FST query or a WFST query, then you could do that. Suggesters, I think there's a lot of stuff we're still exploring with suggesters. There's a lot more work to do there. We want to have a fuzzy suggester so that if someone types WEA, perhaps you want to allow some misspelling within there and autocomplete to some very strong matches. Analyzing suggester, which is a patch in progress that has lots of great capabilities. Multi-word, n-gram suggester. So there's a lot of fun stuff that still needs to happen with suggesters. And then a final example we thought of here is distributed IDF is very important in a sharded environment. You need each shard to share its index statistics with one another so that the distributed scoring is correct or close to correct. And FST would be a great data structure to take the top end most frequent terms, pack it into a byte array, and send that byte array across to all the shards. And of course, patches are always welcome. Okay, so in conclusion, finite-state technology is a really good match for Lucene. Since we've added FST, since we've added Automaton, we've been using it all over the place, and it shows no sign of abating. We have 3 extremely different implementations in Lucene. We saw the very flexible Automaton package, Tinkertoy-like API. We saw the FST package, very restrictive API, confusing, but very low overhead and high scale. You can make immense FSTs with this. Somewhere, we have someone from the Internet Archive who really pushed the limit. There he is. Pushed the limit on the world's largest FST, hit some limitations on the FST APIs that we'll have to fix. So we're using this technology all over the place in Lucene, and I'm sure we've got many more coming. This final cute little automata that you can see here, that's actually the same automata you saw before, but allowing 2 edits instead of 1. So if you allow 2 edits from the word dogs, that thing will accept it and accept nothing else. Questions?
Lucene Solo that seems to touch the FSTs are a very small cadre of people, and I know them. On the surface of it, it's a very simple data structure, a map or a set. So I would imagine that they should be easy to use. Yeah, when I see the API, it looks like I don't know. Is there a direction to make them simpler to use so that I don't need to be an FST expert, but understand the benefits of them and still apply them?
I think we are trying to make the API simpler. The simplest explanation for this is that the FST becomes complicated because you want to parameterize both the input encoding and the output. So you want to be able to plug in this pluggable output algebra. But as well, you want the input encoding to be maybe encoded in a different way depending on your input. Like if we have this Japanese case for Kuromoji, we actually want to encode it as UTF-16. It's more efficient than UTF-8. And it just makes sense because of the type of terms we have, right? But in a lot of cases, UTF-8 may make sense or something of that nature. So things like that, trying to parameterize the input there makes it kind of tricky. I think the many different use cases, different performance trade-offs, I think it's kind of a hard thing to refactor. The steps we are making is like we added examples to the package. So if you look at the documentation now, you'll see there's actually a list of like 4 or 5 use cases in sample code. So here's how you get started. Here's how you do key value lookups. Here's how you do enumerations, shortest path searches, things like that. So hopefully it'll just get better. I mean, the only thing we can do is hope that we get more patches to clean it up.
Yeah, I would say it's really important when people like you try to sit down and look at the FST APIs and improve them or use them. Send us an email about how hard it was. Tell us like what could be improved, because that's how it's going to get better. It's a challenging problem because the low-level format is very, very dense, and it's very much based on arcs. It doesn't have any nodes. A node is wherever its arcs begin, and so that low-level representation is coloring the eventual API that's up on top. It's a very arc-based API. Okay, thank you.